In this video, I look at prime coding. Now, firstly, since we are talking about primes, we define what a prime number is. Firstly, we all know what a prime number is. A prime number which is divisible only by itself and by unity. Only by itself and by, so no other number divides it uniformly. So a number which is not prime is said to be composite. It has divisors. As you might suspect, if a number is composite, it will be composed of prime factors. Right? That means it must be divisible by some number lesser than itself, which in turn must be either prime or composite, and so on. So it is always divisible by some number, prime or composite, less than itself. It has one factor, which is that. So you might suspect. So now this leads us to the the fundamental theorem of arithmetic, which says that every number n can be expressed as a product of primes to their respective multiplicity or factors, powers, p2, k2 and so on, up to there exists k prime, such that it can be expressed in this form. The proof, again, just as I said now, assume that this fact is true for all numbers less than n. If n is prime in itself, then it is automatically true. If n is non-prime, then it can be expressed as a product of two numbers, n0 and n1, where 2 less than equal to n not less than equal to n1, which would imply again that n by 2, both n0 and n1 are less than n, since we have assumed that the statement is true for all values less than n by inductive definition. Therefore, it is also true for n. And this fact, and also that the set of all prime numbers is an endless one, the proof of which you should also be familiar with. If we assume to the contrary that there are only n primes, say p0, p1, p2 and so on up to pn minus 1, then the number obtained by taking the product of all of this and adding 1 to it will also be prime, which is neither a none or not divisible by any of these primes. Hence, the set of prime numbers is always endless, though there could be a lot of other primes in between that, but nevertheless it is impossible. There are, since the number of numbers itself is infinite, the number of primes are also infinite. Now, our interest in prime numbers is only as a way and a means for losslessly compressed coding large amounts of information. To that end, countlessly and compactly. Now here, to that end, I will illustrate one possible method by which it is possible to code large amounts of information losslessly. Consider the first p prime numbers. I will take let p equal to 4. So you will have the set 2, 3, 5 and 7 as the first prime numbers. So we wish to code an information 0 less than equal to n less than m equal to 2 power L dash. Okay. I have taken the set of leading first 4 prime. You can take first p prime numbers, p can be greater than 4 here. For an as a case of illustration, I have taken this. Consider all numbers of the form 2 power alpha naught, 3 power alpha 1, 5 power alpha 2 and 7 power alpha 3. Okay. So we need this to be equal to 2 power alpha naught, 3 power alpha 1, 5 power alpha 2 and 7 power alpha 3 equal to 2 power L dash. Okay. Now since there are 4 factors here, 2, 3, 5 and 7 with their respective powers alpha naught, alpha 1, alpha 2, alpha 3. In all, how many in all 4C0 plus 4C1 plus 4C2 plus 4C3 plus 4C4 equal to 16 combination equal to 2 power 4 or 16 combinations exist. Okay. So now we shall consider each and every one of these cases or combinations. Consider the first case 4C0. This is a trivial case where alpha naught equal to alpha 1 equal to alpha 2 equal to alpha 3 equal to 0. Okay. Now consider the second case, all 4C2 combinations. Therefore you will have you will have 2 power alpha naught, 3 power alpha 1, 2 power alpha naught, 5 power alpha 2, 2 power alpha naught, 7 power alpha 3. There will be 6 of those. 3 power alpha 1, 5 power alpha 2, 3 power alpha 1, 7 power alpha 3 and finally 5 power alpha 2, 7 power alpha 3. So these are the 6 possible combinations. Now for each of these values, for 2 power L dash, we should try and find the bounds of these. Before you get into 4C2, let's do 4C1, I forgot that. So let's, if we take 4C1, we will have 2 power alpha naught, 3 power alpha 1, 5 power alpha 2 and 7 power alpha 3. Okay. So if we require 2 power alpha naught equal to 2 power L dash, we will require alpha naught equal to L dash. If we require 3 power alpha 1 equal to 2 power L dash, we require alpha 1 equal to L dash by log 3 to the base 2. Likewise, if we require 5 power alpha 2 less than equal to 2 power L dash, alpha 2 less than equal to L dash by log 5 to the base 2 and so on. Similarly, alpha 3 less than equal to L dash by log 7 to the base 2. This will be true for 4C1. Similarly, we consider 4C2. For 4C2, there are like we just saw earlier, there will be 2 power alpha naught, 3 power alpha 1, 2 power alpha naught, 5 power alpha 2, 2 power alpha naught, 7 power alpha 3, 3 power alpha 1, 5 power alpha 2, 3 power alpha 1, 7 power alpha 3, and 5 power alpha 2, 7 power alpha 3. So these are the 6 possible combinations. For each of these we try and find a bound. Here we try to find the bound for alpha naught, and for each possible value in the interval over which alpha naught can take, alpha 1 will vary over another interval. So the product of those, like that, we have there will be an interval of value for associated with alpha naught. For each value in that interval, there will be an interval of values associated with alpha 1. It's like a speedometer or an odometer. We have to remember that. Think of it like that. So consider the case 2 power alpha naught, 3 power alpha 1 equal to 2 power n dash less than or equal to. We are interested in numbers of this form. So you will have 2 power alpha naught plus alpha 1 log 3 to the base 2 less than or equal to 2 power l dash. So l dash must be less than or, alpha naught must be less than or equal to l dash minus alpha 1 log 3 to the base 2. Maximum value for alpha naught will occur when alpha 1 is equal to 1. So that should give you alpha naught less than or equal to l dash minus log of 3 to the base 2. Okay. So for each possible value for alpha naught in the interval between 1 and l dash minus log 3 to the base 2, there will be an interval of values associated with alpha 1, where again you will have to vary 1 but maintain alpha naught as it is. So the product of those will be the size of the total number of values or intervals. So all we are doing is trying to construct composite numbers between 0 and 2 power l dash, as many as we possibly can, and number them, so that between two consecutive composite numbers thus constructed, the value of information will always lie, and those values will be pretty close, so you can afford to cut them down very fast. Now consider the other case as well. Similarly, we can do for all 6 of them. When you have 2 power alpha naught, 3 power alpha 2 less than or equal to 2 power l dash. Therefore you will have 2 power 5 power alpha 2, it should be not 3. So 2 power alpha naught plus alpha 2 log 5 to the base 2 less than or equal to 2 power l dash. So that should give you alpha naught less than or equal to l dash minus alpha 2 log 5 to the base 2, again taking alpha 2 equal to 1. Largest possible value for alpha naught will come out to be alpha naught less than or equal to l dash log 5 to the base 2. Again, for each possible value of alpha naught in the interval between 1 and this value, there will be an interval of values associated with alpha 2, which you can compute. So the sum of all those values, product of those two, will give you, or for each value summation should give you the total number of values there. Similarly, I should just consider one more case. Similarly, I'll just mention all the other possible values as well. So if you take 3 power alpha 1 and the last case 7 power alpha 3, or sorry, not the last case, 3 power alpha 1, 7 power alpha 3, one case before that, less than or equal to 2 power l dash. Then again we'll have 2 power alpha 1 log 3 to the base 2 plus alpha 3 log 7 to the base 2 less than equal to 2 power L dash. That should give you alpha 1 less than or equal to L dash minus alpha 3 log 7 to the base 2 by log 3 to the base 2, taking alpha 3 and is equal to 1. We should get the bound for alpha 1, which would lie between, take alpha 3 equal to 1, and then for each possible value of alpha 1 in this interval, there will be an associated interval values for alpha 3, which you can compute by substituting the value for alpha 1 in that expression, and then determine. So the product of those two will be like that. For all 6, you will have an interval, set of intervals, each of which will result in a number which is less than or equal to the given, less than or equal to 2 power L dash. So the set of our next we consider similarly numbers of the 4C3 combinations. There will be again 4 of those. That will be 2 power alpha naught, 3 power alpha 1, 5 power alpha 2, 2 power alpha naught, 3 power alpha 1, 7 power alpha 3, 2 power alpha naught, 5 power alpha 2, 7 power alpha 3, 3 power alpha 1, 3 power alpha 1, 5 power alpha 2, 7 power alpha 3. So these are the 4 combinations for 4C3. So we will now, similarly like we did earlier, we will try and determine. I should just take some one combination over here, say 2 power alpha naught, 5 power alpha 2, 7 power alpha 3 less than equal to 2 power L dash. So you will have 2 power alpha naught plus alpha 2 log 5 to the base 2 plus alpha 3 log 7 to the base 2 less than or equal to 2 power L dash. So we will have alpha naught less than or equal to L dash minus alpha 2 times log 5 to the base 2 plus alpha 3 times log 7 to the base 3. Taking alpha 2 and alpha 3 equal to 1, we will have L dash minus the largest possible value for alpha naught. Alpha naught will lie between log 5 to the base 2 plus log 7 to the base 3. Okay, now for each possible value of alpha naught in this interval, alpha 2 will have, there will be an interval of values associated with alpha 2, and for each possible pair of alpha naught, a specific value of alpha naught and alpha 1, there will be an interval of values associated with alpha 3. So the product of those is what? It will be the size of the interval or the set of all possible numbers generated like this. So now, as we can see, even for us, we are only interested in so finally we come to the last combination, which is 4C4, where we have 2 power alpha naught, 3 power alpha 1, 5 power alpha 2 and 7 power alpha 3 less than or equal to 2 power L dash alpha naught plus 2 power alpha naught plus alpha 1 log 3 to the base 2 plus alpha 2 log 5 to the base 2 plus alpha 3 log 7 to the base 2 less than equal to 2 power L dash. Therefore we will have L naught is less than or equal to L dash minus alpha 1 log 3 to the base 2 plus log alpha 2 log 5 to the base 2 plus alpha 3 log 7 to the base 2. Taking alpha 1, alpha 2, alpha 3 equal to 1, we should get the interval of values for alpha naught upper bound, so 1 less than equal to alpha naught less. For each possible value of alpha naught, there will be in this particular interval there will be a value for alpha 1, and then again for the pair alpha naught alpha 1 there will be a value alpha 2. For each of possible this triplet there will be a value alpha 3. So like that you will have to take the product of those. So for a given L dash, we can choose some number p. Here I have taken p equal to 4 because it's not too many. So we can build up composite number. There will be two composite numbers. This set of all possible numbers generated like this is always an ordered set. The values. So between two consecutive composite numbers thus generated, the information n will lie between those. Then all you have to do is find the least value, say v, of the form 2 power alpha naught, 3 power alpha 1, 5 power alpha 2, 7 power alpha 3, and its next value v dash of the form 2 power alpha naught dash 3 power alpha 1 dash alpha 2 dash and 7 power alpha 3 dash, and take the difference between these two values. You can always subtract this value from the information, so you'll have the new value for m will be log of v dash, ceiling of log of v dash minus v to the base 2 power that 2 power this. New value of L dash equal to this, ceiling of log of v dash minus v to the base 2, and 2 power L dash. Now L dash will be this, ceiling of log. So you can subtract. So not all numbers, some numbers have different. So the larger, the more number of sets you say, it may not be too large, but it can be more than 4. You can, if you can afford to take more than 4, if you use, then then you repeat the process and you iterate this. So to code a single iteration, the number of bits required will be, you have to know the size of this thing. We can roughly estimate it, right? So we can determine L dash also, depending, suppose S is equal to, if you wish to code a number less than m less than equal to, as a value which is less than S equal to 2 power L, then we can determine L dash for a given value of L. Say if you take 32 bits or whatever, then it must be size of alpha naught plus size of alpha 1, size of the interval of all of these values, size of alpha 2 plus size of alpha 3 plus summation of sizes for alpha 1 alpha naught alpha 1 plus alpha 1 alpha 2 alpha naught alpha 2 plus alpha naught alpha 3 and so on. Like that. Finally, you should also have summation for plus summation of alpha naught alpha 1 alpha 2 plus all those values for alpha naught alpha 1 alpha 3 plus summation of alpha naught alpha 2 alpha 3 plus summation of, you have to take summation for each value of alpha naught alpha 1 alpha 2 and alpha 3. Finally the interval for alpha naught alpha 1 alpha 2 alpha 3. So that will be the value of, so which is the, if we can find out the largest value, right, L dash we can try and estimate it. So that this sum always lies between 2 power L. Knowing the bounds for L dash in terms of alpha, not alpha 1, alpha 2. If we require this value to be less than n, we can roughly try and estimate L dash and try and code that L dash information in L and keep repeating that process until the entire information is coded.